I'm going to talk about how to cost effectively and reliably build infrastructure for machine learning. Just a bit about myself. My name is Usman, and I'm a huge fan of performance, reliability, load balancing, scheduling, and cost optimization. Since I've started working in industry, I did my PhD from UIUC, which was mostly related to performance and optimizations for making high performance computing reliable, and I've published a bunch of paper, and I've spoken at both academic and industrial conferences. Currently, I'm working at MIST. I'm their engineering manager, come tech lead, come software engineer, all of them, because it's a startup. I'm working on infrastructure, data platforms, and operations. I've seen our company grow by 10x multiple times. So I've been through days where scalability can become a big issue. So let me just quickly go over what MIST does, and then we're going to dive into what I wanted to talk in this talk. So MIST is a cloud-based machine learning company which is mainly operating in two different domains: Wi-Fi domain and location and in indoor location. In the Wi-Fi, we are basically trying to come up with machine learning models that could help make Wi-Fi predictable and more fault tolerant for big enterprises. We are deployed in a bunch of big Fortune 25 companies, and so that's a play over there. On the indoor location side, you can think of us as the Google Maps for indoors. We would be able to route you through, let's say, grocery stores or museums. You can do proximity messaging based on that. And for any other information, feel free to go to www.mist.com, and you can find more details and more use cases over there. Okay, so here's the MIST architecture. What are we trying to do? We have a truckload of data coming in from our access points, and these access points are deployed all over the world, and there's basically telemetry time series data that comes into SSL terminators. From there it goes on to the Kafka message bus. From the Kafka message bus, there are two compute engines which are primarily doing all the heavy lifting. It's Apache Mesos and Storm. And from there on, we process the data and put the final results in Cassandra. We've recently added Elasticsearch, but it's in kind of semi-production, so that's why you're not seeing it over here as well. And then we have our web services running inside Apache Mesos, and they are serving the end users with whatever computation we are doing. Just to give you an idea of the kind of scale, we are still a small company. We're a startup. We're not getting data in the order of petabytes per day, but we are getting several terabytes per day. This data goes across 500 just different Kafka partitions. Just a rough idea about the number of messages. We are over 10 billion messages per day, and on any given day, we exchange several tens of terabytes of data inside our VPC, which is in an Amazon term, you can think of it as our production data center. So I'll start with a very quick overview of what machine learning we are doing, and then we'll discuss about what is the focus of this talk. So Marvis is our virtual network assistant. You can ask stuff like, what happened with my iPhone this morning at 9 a.m. and it will give you a bunch of results saying that, okay, you were having trouble connecting to the internet at that time, and that was due to a DHCP problem or some Wi-Fi related things that I'm not an expert on, but basically it's based on probabilistic programming. It uses Bayesian statistics. In terms of data, what we are talking about is that there's this data piping in from Kafka. It's going to mainly two frameworks, which is some topologies running inside Apache Storm, and then we have our own in-house time series aggregation system, which goes by the name of Live-aggregators, and I'll discuss more details about them in the coming slides. But that's the high-level picture of what's happening. We have Apache Storm and Live-aggregators bringing in data from Kafka, transforming it, and then we have our inference engine, which applies Bayesian statistics on top of it to create value out of it. Another significant part of our machine learning is anomaly detection. We have a lot of time series data. Like, just to give you an example, we are calculating how much time each Wi-Fi client is taking to connect to the Wi-Fi network, and that figure is basically the time to connect for clients for a particular site. And that's basically, so the idea over here is learn from the pattern and do anomaly detection on these patterns. We are currently using seasonal ARIMA models along with TensorFlows to do this, and we are doing this across multiple dimensions. And so while we were working on anomaly detection a couple months ago, and that's that's not a fairly old thing, it's pretty recent. We were trying to figure out, our data is very seasonal, so we're trying to figure out, should we use, in reality it has a 7-day seasonality because because of the weekends. So we're trying to figure out, should we use our seasonal ARIMA models with 7 days of periodicity, which is the right way to go about it, or how does it compare to a seasonality of 1 day, if you use a seasonality of 1 day. And of course, like, if you use a seasonality of 7 days for our models, the results were significantly better. However, if you look at the costs, we were actually doing this in Python, and I guess we were using stats models, if I'm not wrong. And what we figured out was that by just changing that seasonality parameter, our compute requirements and eventually our cost shot up by an order of magnitude compared to a 1-day seasonality. And we figured out the reasons for it, because the underlying library was using dense linear algebra routines for sparse matrices. But that's the point I want to take home. So what is this talk going to be about? We are going to be talking about how can we cost effectively do machine learning, because machine learning can be very, very cost hungry. So I'm going to talk a lot about this specific contract that Amazon offers, because we are on AWS as well, which is spot instances. I'm going to go in much more detail in the following slides, but I'm going to talk about how do we minimize machine learning cost, or basically data platform cost, by using Amazon spot instances. And while we are doing it, since this particular contract comes with significantly less reliability, how do we cope with these machines going away and coming back? And I'm a big fan of load balancing, and for that reason I spent a lot of time looking at containers that we're running at Mist. How can we right size them? What happens in our infrastructure? This noisy near concept. So I'm going to talk more about how do we go about right sizing containers in our infrastructure, and then about how do we monitor real-time applications in the presence of high failure rates. So let's start with the contract types that Amazon offers. So if you go to the EC2 web page, you'll see that they say that there is an on-demand instance type, there is a reserved instance, and then there's a spot instance. Sometimes it's confusing. What should we do? If you look at, and for that reason I put up this matrix over this matrix over here. So there are 3 dimensions as I see them: a cost dimension, a reliability dimension, and a commitment required dimension. If you go with their on-demand instance type, what that means is they're going to charge you a lot, it is going to be very reliable, and there is absolutely no commitment required. Well, there is sort of a commitment required, because if you spin up a machine, you use it for 5 minutes and you terminate it away, they'll charge you for that hour. So yeah, there's an hourly commitment required over there. If you go to their reserved instance contract, what they would say is that, okay, I'm going to give you a discount. Typically it's in the ballpark of like 25 to 30%, depending on exactly what your contract is. It is super reliable, but it has a commitment. So you'll have to use, or it doesn't even matter, you'll have to pay for that machine for a year or 3 years, depending on the contract. And then they offer this third kind of contract, which is a spot instance contract. This, you can think of this as a bidding platform. You bid for machines and you win the auction and you use the machine. The problem is, when you lose the machine, you just lose it. Typically it comes at a significant discount, but there is no commitment required. So let's talk about what exactly are we talking about. So spot instances are basically unused capacity from EC2. Like everywhere in the world, no one can match demand and supply exactly. So Amazon at the end of the day has a lot of overhead or unused capacity. So what they do is they just auction it out, and it's basically, you go in, you bid for it. Typically they come at a 80% discount. I've seen these machines go up to like at a discount of like 90%. So they're extremely cheap compared to their counterparts, and you exactly get the same machine. It's not that you're getting an inferior machine, you get the exact same machine that you'll get on an on-demand contract. The only deal is if someone bids higher, they're going to take it. But over a period of time, it offers pretty good discounts. However, one caution over here, there are ways to use this type of machine, and I talk about that in the coming talk. However, it's very important to understand how exactly does this pricing work, because if you don't understand the pricing, you won't get the confidence to actually use these kinds of machines. So here are 7 machines in EC2. Let's say there's this machine type R3 which is a 32 core machine with a lot of RAM. So they have these 7 machines. What happens is they get 3 users, user A, B, and C, which are bidding for 3 machines. Let's say user A is bidding for 3 machines, and he's willing to pay $10. And similarly, users B and C are also bidding for the respective prices that I mentioned. So user A gets all 3 machines because he's the highest bidder. User B gets 2 machines because he's the second highest, and user C just gets 2 machines because that's what's left. Although user C wanted 4 machines, he's only getting 2 machines because that's what is left. Then what happens? The spot price. Actually, the important part over here is, independent of what you are bidding on for these machines, you will end up paying the price that the lowest bid, basically the price of the lowest bid that won. So in this case, everyone pays 40 cents. But what happens is, the demand for, someone just came in and said, I want on-demand machines. Let's say I wanted 3 on-demand machines. What Amazon will do is they'll take the 2 machines from user C, and they'll take 1 machine from user B, and they'll just take it like that. I think they've recently started giving a 2-minute warning, but back in like maybe 2 years ago, they'll just take the machine. And like I showed in the previous figure, they'll just take the plug out. And just to give you an idea about what kind of volatility you should expect from these kinds of instances, here is a chart of the number of instances that we at Mist Systems have been losing each day over the last several months. And you can see there was a day when we lost 44 machines, which roughly comes out to be around 25% of our entire production data center. It saves money, but it comes at a cost. So what are we doing? Instead of, given all this volatility, we are running 80% of our production data center on spot instances. Our Mesos cluster and Apache Storm cluster, which is the heart of our system, is 100% on spot instances. That ends up saving us a lot of money, but it allows us to do a lot more, because now within the same cost envelope, we can do much more machine learning that we want. However, the thing that I like it about is it forces us to be reliable. Forces us in the sense that we are not talking about that there is a chance that these machines will go. We are talking about that they will absolutely go. We'll have terminations every hour or most probably every day for sure. So if we think our applications or our infrastructure is reliable, we're going to figure it out. We're going to find it out. So just to give you a comparison of how much money we can save using spot instances. So here's a breakup. About Storm and Mesos together constitute around 80%, more than 80% of our infrastructure. And if we were using on-demand machines, using spot instances, we are saving around 75-ish% on Mesos and Mesos and Storm clusters compared to on-demand machines. Even if we were to go to with RIs, which come at a significant discount, we are still saving more than 60% of our cost. And an interesting statistic that I actually figured out while making this talk a couple of days ago was 17% of our infrastructure, exactly 17% of our infrastructure is not on spot instances, and that constitutes more than half of our cost. And these systems that I mentioned over here, they're not on spot. So we need to, we are currently thinking about moving Kafka and Cassandra on spot. But how do we go about it? How do we use spot instances? So Amazon talks about spot markets, which basically means a combination of the instance type, and they have different instance types like a compute bound machine or a memory bound machine, and an availability zone. So each combination of an instance type with an availability zone is a spot market, and there is and each spot market has its own price. So you can think of it as as a stock in the stock exchange. What we do at Mist is we are using this tool called Amazon Spot Fleet. You can go in and you can say I want 1,000 cores, or you can also talk in terms of VMs. So in this case, the figure on the right shows we requested for 960 cores, and then we also mentioned in the box over there what different types of instances we are ready to use. And we are probably using around 10 to 12 different instance types over here. But why are we using it? The reason we are using it, it's very similar to the stock exchange. When a machine's plug gets pulled out, typically that spot market, that you lose all the instances for that type. And for that reason, you need to diversify the different instance types that you're using, which in itself is a challenge. So what you're saying is we can use compute bound instances, memory bound instances, any kind of instances, and our workload should be able to run on top of it. The other important thing over here is your applications should be able to restart after faults. So once you configure your spot fleet, the other important thing is you will get machines that are terminating. So how do you handle that? When a machine goes away, whatever workload was running on it, what does it do? So you need to over provision your cluster by some margin. And the way we are doing it over here is we are capturing how many machines we lose every 5 minutes. So like this example shows that the maximum number of machines that we lost in a given period of 5 minutes is 9. And the other important thing is, what is the lead time? How much time would Amazon take for me to ask them to give me this machine and for the machine to be ready to use? So the lead time is 5 minutes. So what we do is we're just using a simple heuristic. If the highest number of machines that we have seen going away is 9, then we should be fine if we just keep 9 extra machines in our data center. However, we just chose this magic number of 3. So instead of just 9 machines, we're just taking 27 machines. And this number is basically, it depends on your confidence in not losing the machine, or basically in the data. Maybe someday, we'll do something interesting on this to figure out, do it in a little more scientific way. So the reason that I like spot instances is it's good for the money. It reduces your costs significantly, but it's also helping you to build reliable system. So a lot of you might be familiar with this open source tool called Chaos Monkey, which Netflix introduced. I think it was really good work, and for me that's kind of the pioneering work in chaos engineering. So Chaos Monkey would go in and it will randomly turn off or terminate servers. However, it's done in a controlled manner. You can stop Chaos Monkey, pause Chaos Monkey, restart it. What we are talking over here is we want uncontrolled chaos on which you don't have any control, because my belief is that anytime you have control over losing machines, you'll pause it at times when you should actually test the reliability of your system. So what that means is your applications and your infrastructure should be super ready for faults because you don't control it. A machine can go at any given time. And what I figured out during the last couple of years of using it in production at Mist is there'll be times when the application developers will deploy their applications on these clusters, and right away in the first day or maybe in some cases few hours you'll know that the application doesn't work. It's not checkpointing properly or other problems, and you won't production environment would not even get applications which are not reliable. So that's why I think that it's actually good to use spot instances, because not only they save you a lot of money, they make your infrastructure actually reliable. So but given all that, how do you cope with this unreliability? Like any other company, we at Mist have both stateful and stateless applications. Well, for stateless applications, if you lose a server like a typical web server, it's not a big deal. Another container will come on a different machine, no state required. It'll just start working. For stateful applications, things can be different. So I'll just give you an example over here. So Live-aggregators is our own in-house real-time time series aggregation system. And just to give some context about the scale at which we are running it, it has in-memory state of around 1.2 terabytes, and it's spawning over more than 1,000 different containers or Mesos executors if you're familiar with it. And it's auto scaling, and it maintains pretty cool server utilization of around 60% to 80%, and it's very diverse. We have containers over here which have a memory footprint of 32 MB all the way up to like 21 gigabytes. So what exactly the main important thing that I've seen in stateful applications running on top of spot instances, or in general in an infrastructure which can have servers going away and coming back, what I figured out is that checkpoint is an extremely important thing to have over there. And the way to think about it is that let's say that there is a stream of messages coming in, M2, M3, M4, and M5, like you can see in the figure, and after M5, after the application process M5, you checkpoint the state, and then you go on to process M6 and M7, and then there is a fault. So what happens is you go back to the checkpoint, you restore it, and then you reprocess M6 and M7, which you already did. So I would say that the application is lagging meaning it's falling behind real time, because it restored the checkpoint and it's processing messages which are from the past, which it already did. So we use different techniques for checkpointing. For Apache Storm, we mainly use Redis. For Mesos, we're using a mix of S3 and Redis. But an important thing to take away over here is that once these servers terminate, and you're reprocessing the work that you already did after the checkpoint, you don't need to wait for it for too long. You can give your application more resources, which is shown in the figure on the lower end over there. You can give more resources to your application, and that can and you can make the work done much faster. So your real-time application will lag for lesser time if you give more resources. But what that means is you give it more resources, you take those resources back, or you'll end up with the noisy neighbor problem. So just to give an example of what I'm talking, this figure over here shows the lag, which is how far behind one of our applications is in real time, and all of the figures that I'm going to share from now on are coming from our production system, so they're actually depicting our production applications. So at around 22:10, one of the machine terminated, and what happened was our scheduler keeps check on these applications and whether they are running or not periodically. So the dead not rescheduled part over here is the lag increasing and the scheduler has not detected that this application is no longer running. And then at around 2015, the scheduler reschedules it on a different machine, it restores the checkpoint, and that's why you see the lag. I'm sorry, the y-axis is not very visible over there, but the sudden jump in the lag is basically now you restored the checkpoint which was from 10 minutes ago, and now it's restarting to it's recomputing all the work that it did previously. And the rescheduling recovery is basically it's working fast to get all the work done and getting back to real time. The interesting bit over here is that this is the recovery time is critical, and it's not the same for all the applications. The typical reasons for different recovery times is high message rate. Some applications might have a lot of messages coming in, the type of computation. If you're doing some sophisticated you're training models, and you're using models to make predictions, that can be compute intensive. And also the amount of data that is coming in per message. And this graph shows that one of the machines terminated, and then all these three applications that were running on that machine that got rescheduled on a different machine, and then the gradient at which they are recovering is different, and that's depending on the message rate and the type of computation. So like all other companies, we have good monitoring. We're using SignalFx, Grafana for monitoring, and I'm actually we monitor applications just to see that our real-time applications, how far they are falling behind real time. But I have a very peculiar view about monitoring. I love troubleshooting, looking at metrics and troubleshooting stuff, and getting very very detailed metrics. And just before we dive into metrics detail, here's a concrete example of how do we measure the lag. So the figure shows the incoming messages that we are sending into Kafka, and the lag basically is the difference between the Kafka timestamps for the most recent message to wherever a consumer or an application is. Like for consumer one, the most recent message is that's a shared. If it's one queue and you have multiple consumers, the most recent message over here is at t is equal to 21 seconds. And consumer one at a given time was at t is equal to at message M3 where the time was t is equal to 8. So we can say that this consumer one is lagging by 21 minus 8, 13 seconds. But it's an interesting question that how much lag is acceptable, and it really depends in real time. In context of real time applications, it basically depends on how much real time your application needs to be. Like we have use cases, especially for our indoor location, where we are sensitive to a few tens of milliseconds, all the way up to where we are aggregating data and showing it in the UI, where we don't care much about anything under than a few minutes or a couple of minutes is completely fine. Here's a dashboard of the way we are doing tracking our lags for different applications. So we have some of our most important applications shown on a dashboard, and this is measuring their lag in seconds. The red box over here is one of the applications. Its lag went over probably around 3000, which is like 50 minutes. This is one of our beta applications. So what typically happens is, if you, depending on the application, you set up a threshold. If you cross that threshold, there is an incident which wakes up the on-call person at home. So we have several of these dashboards so these dashboards are basically telling us when there a problem is. And then we have an attribution part. So we are tracking key metrics, just like CPU, memory, IO, like any other company would do. But we are also into fine-grained performance metrics. We are tracking how many CPU cycles is each of Amazon's different instance type taking to consume the exact same stream of message. that I'll show in a couple of slides. And we're using signal effects where you can tag different dimensions to the same metric. Like you can tag which host it's running on, container IDs, service application names, and environments, and all these kinds of different properties. And what that enables you is that you can go in and you can of course filter on any of these tags, or you can also aggregate. You can see that tell me all the total number of CPUs that are being taken for this service that is spawned across hundreds of containers. And here's an example of it. We are in this figure we are tracking the CPU the actual CPU usage for each container that we have in the production. Well, actually I just this is not for all the containers, this is a subset of containers because I didn't want to make it messy. And from here we debug a bunch of our problems, and this is what I was referring to earlier. This data over here is the CPU utilization for consuming the same stream on 7 different instance types in a production data center. And what we figured out was that there are these group of instance types, which are mainly the compute bound and for some reason machines that have disks with NVMe that were faster to consume Kafka compared to this other group over here. And basically from there we get to make intelligent decisions about that. If we are talking about this particular Kafka stream, we should give priority to this Kafka stream to be consumed on this specific instance type. So we can do this at scheduling time, and that can improve the performance of your system. So now what I want to do is to drive you to a case study. So this is an example of one day at work. We can, I think probably I was on call, or maybe I was not. I don't remember. But we got a pager duty. We got a pager duty page on Slack, and we figured out that at 5:15 there was one application which started falling behind real time. And from one particular dashboard, we figured out, okay, which machine, which VM is it running on? We went on that VM's dashboard and we figured out that yes, at 5:15 the CPU utilization suddenly increased, and from here on we went on to a finer detailed dashboard, which is telling what exact containers are running on this service and how much CPU are they taking. So we figured out that there is this location application whose CPU utilization increased at 5:15. So we ended up terminating that microservice so that it can be rescheduled on a different host at 7:15, and then we saw that okay, the lag came down and things were fine. So what's the problem that we just saw was, the noisy neighbor problem, and it's exactly what you're looking in that figure. You have a slot in the aeroplane, and you're trying to fit too big a bag in there, and that's exactly what happens with a lot of containers on Mesos and even on Kubernetes these days. That you have a certain capacity that you can take, but you end up taking more than that. So the way we are dealing with it is that we came up with this metric which we named as lying factor. Lying factor is basically the amount of resources, or in this example, the number of cores that you reserved versus the actual number of cores that you are using. So if you reserve 1 core and you end up using 2 cores, you have a lying factor of -1, which is bad because you are the noisy neighbor in that case. So like I said, a negative number means it's dangerous. It can cause hotspot. Like in that figure over there, the 2 red dots are the hotspot. And if those 2 VMs are running some API, some very highly critical API, you're screwed just because of the two VMs. So hotspots and noisy neighbor thing is a huge problem, and typically people solve it by over provisioning their data centers. But on the other side, if your lying factor is positive, that means reserve minus actual. You are reserving much more than you need. You end up wasting a lot of money. Ideally it should be 0, but it would never be 0. We started by manually tweaking these numbers and making our containers right size, but that won't work. We are a startup. We are growing week over week, our load even changes over the course of a day. So this figure shows that our overall trend for our load is up to the right, and we also have daily seasonality in it. So we can't base our system on someone manually going in and tweaking these numbers. So we came up with an auto scaling mechanism, which is basically you define a lying factor an upper threshold and a lower threshold. If you cross the upper threshold, you're wasting money. If you fall beneath the lower threshold, you are running at the risk of causing the noisy neighbor problem and causing hotspots in your infrastructure. This is an example taken from our in-house live aggregator time series aggregation system, and what you see over here is the line factor for all the 1,000 containers that we run in a production data center. And the highlighted line represents that the line factor it starts at 0.35, which means that it is reserving 0.35 more core than what it really needs. But as the load comes in at 9 o'clock, the line factor goes down to 0. But when the load goes away later on, the line factor once again goes to 0.35. This is an interesting case. What happens over here is the line factor is 0.17. When the load comes in, it touches the lower bound, which is our threshold, which is minus 0.1. It touches that, the container gets terminated automatically, and then it learns that, okay, this particular application was taking these many cores, so it right sizes the container. It gives it more resources and restarts the container. Similarly, when the load goes away, the line factor moves from 0 in the highlighted line over here. It moves from 0 to 0.6, which is the upper threshold, and at that time an auto scaling mechanism detects that now it's wasting a lot of resources. Let's terminate it and restart it. And once again, when we terminate and restart, it's always starting from a checkpoint. And here's what we get. The pink line over here shows the reserved cores for our aggregation system, and the blue line actually represents the real usage, the actual number of cores that we are using. And this is over a course of a day. And like you can see, when in the morning time we scale up, the load increases, our reservations go up, the actual usage is also going up, and then you can see the downsizing over here. After the peak time has passed, the containers start downsizing, and that's how you free up more cores. And in future, we are trying to bring the auto scaling mechanism that we just discussed, not only with our real-time aggregation system, but for our API as well, and other services that we run. We're also looking to use pod instances for Kafka and Cassandra, because they require a lot of money to run, and they're not as reliable as the rest of our infrastructure, simply because we haven't really tested it, that what happens when when the machines go away. It's happened. There have been instances when our Cassandra boxes, they have the underlying boxes have acted up, but it's a much more painful activity, and so for that reason I want it to happen every few hours, so that we get comfortable with it, and things go on fine. And yeah, we are looking for site reliability engineers and data scientists. Please let me know if you guys are interested, and I'll take any questions in a few minutes that we have. Yeah. So is the question, how are we doing the snapshotting? Basically checkpointing. Okay. Yeah, so checkpointing is done in different ways. Like for our Apache Storm topologies, we are, there is not a lot of state, and developers are using Redis to keep the state in there. For our time series aggregation system, since it has a ton of state, it's over a terabyte, we are checkpointing it in S3. Any other questions? Yeah.
I was curious, earlier on you said you were processing messages and you could understand this instance type goes better with this type of message. So that was all based on the same kind of message. Is that right?
Yes.
So have you ever done anything with like different types do better with which types of?
Yeah, that's very good. Let me repeat the question. So the question was that I showed a figure which says that the same Kafka stream is being run on different instance type of Amazon. So have we compared different loads, some other Kafka stream or some other application over different instance type? The answer to that is we just recently started with it. We just looked at one of this and that got our interest. So right now we don't even have an automatic mechanism that's doing it. Right now we are kind of doing it manually. But yes, that's definitely the intent over there, that we figure out that okay, this is your location engine which is compute bound. It should go to compute bound a C3x large from Amazon compared to a different workload. Yeah. Okay. More questions? Was there another question? Okay. Thank you guys. Thanks a lot.